Now that you know the basics on stoichiometry, let's move on and talk about limiting reagents, reagents in excess, etc. Now, I don't have time in a 15-minute YouTube upload to go through all these definitions with you. So I encourage you, if you do not have these written down, that you write them down now, pause the video, write them down now, and make sure you understand the meanings before we continue on with the video. It's very important to understand that limiting reactants are the reactants that limit the amount of products that you can make in any chemical reaction. When you talk about theoretical yield is always calculated from the limiting reactant because it is the amount that theoretically could be formed from the limiting reactant if all of the reactants were converted into products. You do need that theoretical yield in order to calculate the percent yield, which is the actual or experimental yield over the theoretical yield times 100. Again, if you need to review these definitions, please pause the video and make sure you have all the definitions written down and understood before you continue. So let's move on now to our first example. In example 1, we have aqueous sodium hydroxide reacting with carbon dioxide gas to produce solid sodium carbonate and liquid water. The first thing I need to do, of course, before I can do any calculations, is figure out my balanced chemical equation. So first of all, I have sodium hydroxide, an ionic compound. I know that Na will have a charge of +1 and OH -1, so I'm balanced in that formula at like so. And we're reacting here with carbon dioxide gas, CO2, to produce sodium carbonate and liquid water. Sodium again has a charge of +1, carbonate a charge of -2, which means I need 2 sodium here to balance my formula. Excuse me. That we're told is a solid, and our other product is liquid water. Now let's go back and balance the equation overall. I'm going to look first at my oxygen and see that I have 3 oxygens here and 1 here for a total of 4. I have 2 oxygens on my carbon dioxide and 1 here. I'm going to put a 2 in front of my sodium hydroxide. I have 2 sodiums here, 1 carbon, 1 carbon. Now let's take a look at the hydrogens. I now have 2 hydrogens here and 2 over here, so we have a balanced chemical equation. So my first question asks, what is the limiting reagent when 1.85 moles of sodium hydroxide react with 1 mole of carbon dioxide? You can do this one of 2 ways, and a lot of students think this is the easiest method, the first one I'm going to show you. Let's use our coefficients in the balanced equation to see how many moles react with how many moles. If I have 1.85 moles of sodium hydroxide, and I need 2 of them according to the balanced chemical equation, it means I have 0.985 moles. Reacting with, I have 1 mole of CO2, and the coefficient here from the balanced equation is 1, which means I'm still at 1 mole carbon dioxide compared with every 9.985 moles of sodium hydroxide. So now we can just look at the lowest number here. 0.985 is clearly our lowest number, and therefore sodium hydroxide is our limiting reagent. Let me show you just one other way that this can be done. If we have, and you can start with either one of these amounts given, doesn't really matter. It'll work out the same either way. If I have 1.85 moles of sodium hydroxide, I'm just going to take a conversion factor here and compare it to my carbon dioxide. Using my balanced equation, I know that 2 moles of sodium hydroxide react with every 1 mole of carbon dioxide. So what this conversion factor is telling us is that for every 1.85 moles of sodium hydroxide used, we would need 0.985 moles of carbon dioxide to completely react with it. Now you have to go back and look at what you were given. You have 1 full mole of carbon dioxide, and if you use this whole 1.85 moles of sodium hydroxide, you'd only need 9.85 moles of carbon dioxide. Do you have that much? Yes, and extra. Therefore, carbon dioxide would be your reagent in excess, and sodium hydroxide would be your limiting reagent. So the next question asks us, how many grams of sodium carbonate will be produced in this reaction? And that's actually our theoretical yield. Remember, theoretical is the maximum amount that you could possibly get if all of the limiting reagent were used up. So you always have to start with the amount of your limiting reagent. The limiting reagent we decided is sodium hydroxide. Therefore, I'm going to start my conversion factor with 1.85 moles of NaOH. Now we're starting with sodium hydroxide, and we need to get to sodium carbonate. So I'm going to use the mole-to-mole ratio from the balanced chemical equation here in order to convert from moles of sodium hydroxide into moles of sodium carbonate. So I know I have 2 moles of sodium hydroxide for every 1 mole of sodium carbonate. Now my moles of NaOH canceled here, and if I stop now I'd be in moles of sodium carbonate. But I need to get to grams, so I'm going to take it one more step. For every 1 mole of sodium carbonate, if you go to your periodic table and calculate the molar mass, you should find that there are 105.99 grams of sodium carbonate. Check that your units are canceling properly. And right now, if I calculate this out, I'll be in grams of sodium carbonate, which is exactly what I'm looking for. And your answer is 98.0 grams sodium carbonate. So the next part of the question asks us, what mass of the reactant in excess remain when the reaction is complete? Remember that we determined that sodium hydroxide was our limiting reactant and carbon dioxide gas was our reagent in excess. So we need to start with our amount of sodium hydroxide, which was 1.85 moles of sodium hydroxide. Using the coefficients from the balanced equation now, I can use my mole to mole ratio to compare my moles of sodium hydroxide to my moles of carbon dioxide. And from the balanced chemical equation, that ratio is 2 to 1. Now I need to convert from my moles of carbon dioxide, which I'd be in right now, into grams of carbon dioxide. And we know that in every 1 mole of carbon dioxide, there's 44.01 grams of carbon dioxide. So if I stop right here, you can see that I'm in grams of carbon dioxide. If you run that through your calculator, you're going to find that your total is 40.7 grams of CO2. Now the question actually asks, what mass remains when the reaction is complete? And this is actually the amount we used. So I need to go just one little step farther. Since we started with 1 full mole of carbon dioxide, meaning 44.01 grams, and I used 40.7 grams, it means I have a remainder of 3.31 grams of carbon dioxide gas. Let's look briefly at the last part of the problem. It asks you if 93.5 grams of sodium carbonate are actually produced, what is the percent yield? The percent yield equals the theoretical yield over, is the actual yield over the theoretical yield times 100. I'll have you calculate that, and you can check your answer in the first part of the next video.